Okay, let's practice some calculations for hydrogen ion concentration, hydroxide, pH, pOH. Make a determination as to whether the solution is acidic or basic based on those calculations or what we can observe. And in doing so, we want to use all of these 6 tools plus our 2 constants, the kW and pKw for water at 25 degrees Celsius. So here we go. So the first row, and I'm going to call this row 1, and then row 2, row 3. Let's see, let's call this row 4. Okay. And so I'm looking at row 1, and I'm seeing that the hydrogen ion concentration is 7.5 times 10 to the minus 3. I could go ahead and calculate the hydroxide ion concentration using this equation, but let's go ahead and do the simplest thing. Since I've got the hydrogen ion concentration, let's calculate the pH using pH equals the negative log of the hydrogen ion concentration. So this will just be pH is equal to the negative log of, what do we got? 7.5 times 10 to the minus 3. So that's 7.5 times 10 to the minus 3 molar. That's a 3. Now let's make some predictions about this. If the hydrogen ion concentration were 1 times 10 to the minus 3, then the pH would just be, pH would equal 3. But it's slightly higher. Actually, it's halfway to 10 to the minus 2. So as the hydrogen ion concentration goes up, pH goes down. So the lower the pH, the more acidic the solution. And so we know that the pH is going to be 2 something, and actually a fairly low 2 something. So when we plug that in the calculator, negative log of 7.5 times 10 to the minus 3, I wind up with a pH of 2.12. Now, since I've already got the pH and it's less than 7, I can go ahead and say this is an acidic solution. I don't need any other information to make that prediction. To get the pOH, I think I'll use this equation right here. pKw equals pH plus the pOH. The pKw at 25 degrees Celsius is 14. So that's just going to be 14 minus 2.12. So 14 minus 2.12, and I get 11.88. So my pOH is 11.88. To get the hydroxide ion concentration, I think we'll use Old Faithful here. Kw equals H plus OH minus. I'll use something else next time. So the what I want is the hydroxide ion concentration. And so all I'm going to do here is divide Kw by the hydrogen ion concentration. Kw is 1 times 10 to the minus 14, and the hydrogen ion concentration is 7.5 times 10 to the minus 3 molar. So I'll plug that in. 1 second. E minus 14 divided by 7.5 second E minus 3. And I get 1.3 times 10 to the minus 12. So that's going to give me 1.3 times 10 to the minus 12 molar in hydroxide ion concentration. Okay, so that takes care of line 1. Let's do row 2 over here. Now what they give me is the hydroxide ion concentration. And let's use Old Faithful to get the hydrogen ion concentration. So the hydrogen ion concentration is equal to the Kw, which is 1 times 10 to the minus 14 divided by 3.6 times 10 to the minus 10. So that's 3 5.6 times 10 to the minus 10. We'll plug that in the calculator. 1 second e to the minus 14 divided by 3.6 second e to the minus 10. And that's going to give us 2.8 times 10 to the minus 5. So 2.8 times 10 to the minus 5 molar in hydrogen ion concentration. Let's see. Let's go ahead and get the pOH by taking the negative log of the hydroxide ion concentration. So that's pOH is going to equal the negative log of 3.6 times 10 to the minus 10, 3.6 times 10 to the minus 10 molar. So negative log 3.6 second e to the minus 10. And that's going to give us, and you can make this prediction that the pOH is going to be less than 10, because if it were 1 times 10 to the minus 10, the pOH would be 10. But it's slightly higher than that. And so that's going to give us, it looks like 9.44. So our pOH is 9.44. And we can go ahead and just get the pH with the pKw, which is 14, minus the pOH of 9.44, 14 minus 9.44, up, 14 minus 9.44, and that gives us 4.56. So that's going to give us a pH of 4.56. Now, if the pOH is greater than 7, that means that the pH has to be less than 7, and we know that our solution is acidic as well. Okay, and that takes care of row 2. Row 3, this time we're given a pH. What haven't we used? Let's get the hydrogen ion concentration from the pH using this equation. Hydrogen ion is equal to 10 to the minus pH. The pH is 8.25, so we're going to do the hydrogen ion concentration. That's going to be 10 to the minus 8.25. That's the minus pH. And people all the time forget to put the negative sign in there. If you forget that, you're going to get a ridiculous number, so don't forget it. So that's going to be second log minus 8.25, and I get 5.6 times 10 to the minus 9. So that's going to be 5.6 times 10 to the minus 9 molar in hydrogen ion concentration. Let's go ahead and get the pOH. By simply taking 14, the pKw, minus 8.25. And so 14 minus 8.25, that gives me 5.75. So my pOH is 5.75. Now, our pOH is less than 7. Our pH is greater than 7. So we know that this solution is basic. All right, and to get the hydroxide ion concentration, why don't we use this equation right here, 10 to the minus pOH. So our hydroxide ion concentration is equal to 10 to the minus, and the pOH is 5.75. And so that's just going to be second log minus 5.75. And that gives me, it looks like 1.8 times 10 to the minus 6 molar in hydroxide. 1.8 times 10 to the minus 6 molar, and that's in hydroxide ion in our basic solution. Last but not least, well, we know that this solution is basic because the pOH is less than 7, which means the pH has to be greater than 7 because we're going to be subtracting this from 14 to get the pH. So we can go ahead and call this a basic solution right now. And 14 minus 5.7, and that gives me 8.30. So I know this is 8.30. And I can go ahead and, well, it looks like I'm stuck with getting the hydroxide ion concentration by doing 10 to the minus POH. So that's going to be 10 to the minus 5.70. And so, second log minus 5.7. And that gives me essentially 1.995 times 10 to the minus 6. I'll just call that 2.0 times 10 to the minus 6 molar in hydroxide. I'll go back to Old Faithful and say the hydrogen ion concentration is equal to Kw 1 times 10 to the minus 14 divided by the hydroxide ion concentration, 2.0 times 10 to the minus 6. So let's do that. So 1 second e to the minus 14 divided by 2.0 second e to the minus 6. And that gives me 5.0 times 10 to the minus 9 molar in hydrogen ion. So what I recommend that you do is you make sure you know all of these equations. I'm not sure they're all on the equation sheet. I'll take a look. But you should know them anyway. If you have to look them up every time you try to do a problem, you're going to run out of time. And it's just not that much to know. To know these 6 equations, to know that the Kw of water is 1 times 10 to the minus 14, even though it's on the equation sheet. The pKw is the negative log of this, which is 14. Try solving for these values, which are all in your PowerPoint notes. Try solving for them with different methods. Use all the methods at some point in time. Okay? Okay. Measuring the pH, there you have qualitative measurements, which can actually be fairly good with litmus paper or indicators, a pH meter, and this is a pretty old pH meter. I don't think this is the standard in the industry anymore. It's still a good pH meter, but it takes a lot of time to calibrate using a buffer, which uses the electrochemical potential, measures your hydrogen ion concentration based on this gradient of concentration. And it's very precise. It gives you very good readings. Most of the time, actually, I think the labs now have pH meters, which you'll probably use. But most of the time in titrations, you wind up using an indicator. And so here are a variety of indicators that you could use doing titrations. These are organic acids that change color. Bromothymol blue, sometimes called universal indicator, has a range of colors from acidic, where it's yellow, to blue, and its pH is somewhere between 6 and 8. So if I were going to titrate an acid or some sort of an acid-base concentration to a pH of somewhere in the neighborhood of 6 to 8, I would want to use something like bromothymol blue. If I were going to titrate something to, let's say, a pH of 8 to 10, I could use thymol blue. That would work, and I could also use phenolphthalein. So the different indicators, you generally have a chart, and you just look at the different pHs relative to the color changes of the different indicators. And you can pick the appropriate indicator for your particular titration, depending on the pH that you want to get to. You need to memorize your strong acids. You were supposed to in Chem 1. If you've forgotten, please remember them: hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, chloric, and perchloric acid. You don't have to pay any attention to equilibrium values for these because the equilibrium constants for all of these are extremely product favored. That means that the products, which are H plus and the anion, are just huge, like 1 times 10 to the 7th, 10 to the 10th. Very, very strong, very product favored. So you don't need to worry about equilibrium with acids. So taking a look at that, recall that strong acids completely dissociate in dilute solutions. What is the pH of a solution? That's 1 times 10 to the minus 3 molar. Well, here's the deal, guys. If this is my acid, HCl, which is a strong acid, and it virtually completely dissociates. I can't remember exactly what the K value for this is, but it's on the order of 10 to the 7th. That means that if I've got a 1 times 10 to the minus 3 molar concentration of hydrochloric acid, it's essentially going all the way to products, and I'll have a 1 times 10 to the minus 3 molar concentration of hydrogen ion. The chloride ion is a spectator ion in this dissociation. It's inert. It's not going to do anything. So I can get the pH by going straight to the hydrogen ion concentration and taking the negative log of that hydrogen ion concentration, which is 1 times 10 to the minus 3. And since it's 1 times 10 to the minus 3, all I'm doing is pulling that out and the exponent out, and my pH will be 3. Okay, that's for your strong acids. All right, strong acids, whatever the concentration of the acid, that's your concentration of hydrogen ion in dilute solution. Just go ahead and take the negative log of that concentration. You got yourself a pH. Remember your strong bases. There are 8 of them. Those are the alkali metal hydroxides and calcium, strontium, and barium hydroxide. So we treat these as complete dissociations, but for the heavy alkaline earth bases, remember, you've got 2 hydroxides per mole of the base. And so it's a twofer. So if this were 1 times 10 to the minus 3, your hydroxide ion concentration would be 2 times 10 to the minus 3. So here are your strong bases, okay, all 8 of them. The alkali metal hydroxides, calcium, strontium, and barium, these are the ones that get you into trouble. You have to remember it's a 2 for 1. Okay, so taking a look at that, here's your strong base. We got calcium hydroxide. It's going to dissociate completely into calcium 2 plus aqueous plus 2 hydroxide ions aqueous. So if this is 1 times 10 to the minus 3 molar, then this will be 1 times 10 to the minus 3 molar, but we're not concerned with it because that's not changing the pH of our solution, but this is. And we've got 2 of them, so that's going to be 2 times 1 times 10 to the minus 3 molar. And that's going to give us 2 times 10 to the minus 3 molar in hydroxide. So what we're going to do to get the pH is we're going to calculate the pOH, which is the negative log of 2 times 10 to the minus 3 molar. It's in hydroxide. That's going to give us the pOH. Let's go ahead and do that. And so negative log 2 second e to the minus 3. That gives us, I'm going to round that to 2.70. But that is my pOH. To get the pH, I remember that pOH plus pH equals pKw, and pKw is 14. So I'm going to subtract 2.70 from that, and I get 11.3 0. It would make absolutely no sense to calculate a pH of a base and get a pH that's less than 7. It's a base. It's going to, if you put it in pure water, it's going to make the pH high. Bases make aqueous solutions pHs go up, not down. Okay? All right.